This is a walkthrough of Problem 3 on Exam 1 of Module 5 in the book Problem Solving Guide for Mechanics and Thermodynamics. We have a 10 kilogram cinder block attached to an elastic cord. The stiffness of the cord is 600 newtons every meter. The cord is attached to the ceiling. The block is released from rest. It stops when the cord stretches 10 meters. What is the relaxed length of the cord? How fast was the block going when the cord was stretched 1 meter? There's the good diagram, but let's add the final situation because we have to see what's going on. It really helps. So there's the mass, rest, it's at rest. The cord just stopped it. The cord is stretched some 2 meters and it fell some distance before it became taut, and we don't know what the relaxed length of the cord is. Let's put the stretch and the relaxed length on the diagram to help us understand what's going on. So there's the stretch, and there's the relaxed length of the cord. We don't know what it is. Our diagram might not be to scale, but this helps us solve the problem. The block starts at rest at the top, V initial equals 0, ends up at rest at the bottom. The total work done by all the forces on the block must be 0 because the change in kinetic energy is 0. We can get the work done by the cord. We know the stretch and we know how stiff the cord is. It's 1/2 kx squared, and we put a minus sign in there to remind us that the cord is slowing the mass down. The cord is against the motion. That's minus 1200 joules. The stretch is 2 meters. The stiffness is given 600 newtons every meter. The block started at rest, ended up at rest. Total work done on it must be 0. We know the cord did minus 900 joules of work. We're ignoring air drag. Gravity must have done plus 1200 joules of work. The work done by gravity is the force of gravity, mg, times the change in height. mg delta y, it's falling down, that's positive. Gravity's doing positive work. Gravity's speeding it up. It's moving in the direction of the force. So we can solve this for delta y. The weight of the mass is 100 newtons, and delta y is 12 meters. So we're not done yet. We got to keep thinking, keep your mind on the whole time. If the block fell a total distance of 12 meters and the cord stretched 2 meters, the relaxed length of the cord must be 10 meters. So the answer to part A is 10 meters. Now part B, we want to know how fast the block was going when the cord was stretched 1 meter. Let's draw that. Let's change the diagram so we can see what's going on. All right, so now we're going to look at this. Now it's moving still. We don't know how fast it's going. The relaxed length of the cord is 10 meters. It's stretched 1 meter. How fast is it going? That's part B. The total work done on the block is its change in kinetic energy, and we can calculate both of these. The work done by gravity over the 11-meter fall, mg delta y is 11 meters. The work done by gravity is positive 1100 joules. The elastic cord has done negative work because it's slowing it down. The work done by the tension in the cord, 1/2 kx squared. X is only 1 meter this time. That's the stretch of the cord. So we get minus 300 joules. Gravity made a deposit of plus 1100. The cord took away 300 joules. The total work done on the block is plus 800 joules. And there's some kinetic energy in the block as a result. And we can calculate this. V initial is 0 at the very top. We know the total work done is 800. We have one unknown, and that's the final speed. And solving for the final speed, we get 12.6 meters per second, and that's the answer to part B. But let's explore some more. During the first 10 meters of the fall, the cord is slack. The block is in free fall. It accelerates 10 meters per second each second. When the acceleration is constant, we can use this equation, V final squared equals V initial squared plus 2ay, to get the speed of the mass after it has fallen 10 meters, and the result is 14.4 meters per second. It's important to realize that once the cord becomes taut, the force it exerts is a function of how far it is stretched, and thus the acceleration of the block is not constant. The force is changing, it's getting bigger. If the force is changing, the acceleration is not constant, so those equations are out the window. Those equations were derived from equations that assume the acceleration is constant. So that's no good once the cord is stretching. This is not a challenging problem for a student to draw a good diagram and invest time thinking about what's going on, thinking about what makes sense, being careful. Students who like to rush, plug numbers into equations without thinking are not likely to experience success in this problem. This is consistent with jobs in the real world. Employers, which should be your goal to be an employer, not an employee, employers are people who know the importance of thinking and problem solving. Employers want employees who can think and solve problems. There's not many jobs that say we need people who can mindlessly plug numbers into equations without knowing what they are doing. That's what computers do. That's problem 3.